The exact energies of this molecular Schrödinger equation depends on both lambda value and the S value. So we can write the electronic energies depend on S and lambda. So S means spin multiplicity, so that solutions of this equation for the energies are different if either S or lambda is different. And similar to the atomic term symbol, we have molecular term symbols. In general, it has this form, where letter code for lambda is used here. You see, this expression, this term symbol expression, is very, very similar to atomic term symbols. The only difference is, instead of L quantum numbers, we use the lambda, one of these symbols here. So if we apply this to the hydrogen molecule, we have just two possibilities for S. S is either 0 or 1. S equals 0 means a singlet state, singlet spin, and S equals 1 means a triplet spin. So we have such terms. If lambda is 0, we have sigma states, singlet sigma, triplet sigma. If lambda is 1, we are talking about pi states, singlet pi, triplet pi, etc. These are the possible term symbols for the electronic states of H2 molecule. All right, so far we have discussed exact properties of this equation regarding the spin, total spin quantum number, and also the property related with the z component of orbital angular momentum. Now, the third exact property we know is Pauli principle. The electronic wave functions must obey the Pauli exclusion principle. Now, what does Pauli exclusion principle tell us? That the state function must change sign when any two electrons are exchanged. Here we have just two electrons. So the Pauli part is very similar to the discussion about helium atom. In helium atom, we have also just two electrons. Now, there we had seen that the full function can be written for two electrons, exact psi can be written as a product, a space part times spin part, And the spin part, the spin factor, same as in helium problem. There are just 4 possible 2-electron spin functions. What are they? Alpha times alpha, beta times beta. These are symmetric in spin exchange, alpha times alpha, beta times beta. Or let us write alpha times alpha, beta times beta. And there is a third one, alpha times beta plus beta times alpha. These are symmetric in spin exchange. In any such expression, when the spin part is one of these functions, the space part must be antisymmetric with respect to electron exchange, exchanging their space variables. These are triplets. That means S equals 1. And the fourth spin function is alpha times beta minus beta times alpha. This expression is anti-symmetric with respect to spin exchange. This is, of course, for S equals 0. S equals 0 means 2 times S plus 1 is 1, singlet. So, now we can define what kind of property the space part should have. If the spin part is a triplet spin function, one of these 3, because these triplet spin functions are symmetric with respect to spin exchange, the space part, psi space, must be anti-symmetric with respect to electron exchange. On the other hand, if the spin factor here is a singlet spin function, which is alpha times beta minus beta times alpha, in that case, the space part must be symmetric with respect to electron exchange, because the Pauli principle requires that when all variables, there are 4 variables for each electron, 3 of them are space variables, the 4th one is spin variable. When all 4 variables are exchanged between the 2 electrons, then the total wave function must change sign. It must be antisymmetric with respect to complete electron exchange. To do that, these are the possibilities. For if the spin part is a triplet spin function, space part must be antisymmetric. On the other hand, if the spin part is this term, which is antisymmetric with respect to spin exchange, in that case, space part has to be symmetric. These are the exact properties we know about the solutions of this Schrödinger equation here. And when we do any approximation, we must be careful to obey these exact properties. All right. Now let us come back to this equation here. using the full expression here, in solving this equation is a very complicated, difficult job. So what we do is we employ some approximation. And the approximation starts with dropping the troublesome electron-electron interaction term. So this term, as I said before, is just a constant. Its value can always be added after solving this equation, whether approximately or exactly. What is the real problem is the electron-electron interaction term. If we drop this electron-electron interaction term, we obtain what we call the core Hamiltonian, molecular core Hamiltonian, which is just these two terms. And this Schrödinger equation is very easy to solve. Psi core equals E core times psi core. Because the Hamiltonian is separable here, how do we understand whether it is separable or not? We examine the expression. There are just two terms. The first term contains variables of electron 1 only, and the second term contains variables of electron 2 only. Whenever this is the case, the Hamiltonian is separable. It means the total energy is a sum, and the total state function is a product. And the energies, E core is energy of electron 1 plus energy of electron 2, and psi core is an orbital psi 1 for the first electron times another orbital for the second electron. I call these psi 1 and psi 2 orbital because of the definition that any state function for a single electron is called orbital. That's a general term. The orbitals are obtained, H1 and H2 have identical mathematical structures except for the label. In H1 we attach number 1 for the electron. In H2 we attach number 2 to the same expression. What is the expression? It is this. Minus 1/2 del square minus 1 over RA minus 1 over RB. If you take this expression and attach 1 to all the symbols, here, here, and there, you will obtain what I have called H1 here. And similarly, if you attach 2 to the symbols, 2 here, 2 here, 2 here, you will obtain H2. The mathematical structure is the same. All right? So the energies E1 and E2 are the energies obtained from this equation. H psi equals, I didn't use, oh, okay. Let me write F's times psi. The solution of this equation. Now, if you look at examine the expression for this small h Hamiltonian, we see that it contains variables of just one particle. all right? And therefore, this psi function is a function of just one particle. In this case, the particle is an electron. Whenever we have a single electron, and the state functions for a single electron are called orbitals. This is one electron, Hamiltonian. So this is a one electron function. This is a one electron energy. When we have just one particle, and if that particle is an electron, then we give a special name to the state function of a single electron. We call it orbital. So this psi is orbital. And the energy here is orbital energy. Now we remember that this electron is in a molecule, a one electron in a molecule. What does it mean? We have more than one nuclear center, and as a one electron moving around the two centers. We attach molecular, the term molecular. So we call this molecular orbital. And this is molecular orbital energy. These are our terms. Now, even though this equation with this Hamiltonian is a one electron Schrödinger equation, exact solutions of this equation are not easily found, in contrast to atomic case. In atomic case, for a single electron, we have the hydrogen-like atom. Here also we have just one electron, but what's the difference? In an atom we have just one nucleus, but here we have how many? Two nucleus. That makes it more difficult here. However, we know certain exact properties of the solutions of this problem. Let us indicate our z-axis again. Z-axis is this. We have just one electron here. This is our Lz operator for a single electron. Eigenvalues of Lz for a single electron are m values. Lz commutes with that h. This means that the solutions of this equation, psi, must also be eigenfunctions of Lz operator with eigenvalue m. And the m values are as we have indicated here. Now, as in the many electron case, where these total energies depend only on lambda value and s quantum number, here For the single electron, there is just one S value, it is 1/2. But many different M values are available. Energy, orbital energies, molecular orbital energies, depend only on the absolute value of this small m. We call lambda the absolute value of m. Notice the symbol. This is lowercase of this symbol. This is uppercase. Here we are talking about a single electron. For a single electron, we use lowercase symbols. As in here, for the values of lambda, we have Greek symbols, but in lowercase symbols. So lambda values are 0, 1, 2, etc. Letter. What is the lowercase of sigma? Which symbol? It is this symbol, lowercase. For lambda equals 1, lowercase of pi looks like same as in uppercase, but just the height is small. Pi. Lambda equals 2. This is uppercase delta. What is lowercase delta? It is this symbol. Similarly for 3, phi, these are lowercase Greek symbols for a single electron. So, as in any Schrödinger equation, there are infinitely many solutions of this equation for psi and for the energy Fs. The psi functions can be characterized by the lambda values over there. So each orbital orbitals have symbols sigma, pi, delta, etc. Sigma orbitals are non-degenerate. It follows from this fact. Orbital energies depend on lambda, but lambda is absolute value of m. For m equals 0, there is just one orbital, which we call sigma. So there is only one orbital energy. But if lambda is 1, then m could be either +1 or -1. That means two orbitals with the same energy. They are called pi. In fact, we can label one of the orbitals as pi1, the other as pi -1. This is indicating the m value. Both of these orbitals have the same energy. So what does it mean? The term we use is degeneracy. How many orbitals are there with the same energy? 2 orbitals. One is pi 1, the other is pi minus 1 with respect to m. Doubly degenerate. Same thing is true for delta. There is delta m is 2 or minus 2. So, as you see from this expression, sigma molecular orbitals are non-degenerate. There is just one sigma orbital with that energy, but all the others, pi, delta, phi, etc., are doubly degenerate. These symbols are for complex MOs. As in atoms, you see pi, delta molecular orbitals correspond to PD type atomic orbitals. In atoms, instead of using the complex orbitals P1, P0, P minus 1, we are allowed to use real orbitals, which we designate as P sub x, P sub y, P sub z. Similar to that, in the molecular orbital case, we may use either complex type orbitals like this or real type molecular orbitals, which are designated by pi x, pi y, and here also delta x, delta y type, etc. These are real MOs. Instead of this pair of orbitals, we may use the real values molecular orbitals. The number of molecular orbitals cannot change, of course. There are 2 orbitals here. We must have 2 orbitals of the real type. Now, when we use the real type molecular orbitals, they have an important property which is directly related with lambda. And the property is nodal plane. We have discussed what's a nodal plane before, but let me remind you again. A nodal plane is a plane on which a function has 0 value everywhere on the plane. That's a nodal plane. The nodal planes of main interest in molecules, linear molecules, are planes which contain the z-axis. You have to remember what is the direction of z-axis. Z-axis is a line which passes through all of the nuclei in a linear molecule. Say, this is acetylene, isn't it? C2H2. This is a linear molecule. The line passing through all of the atoms is called Z. So a diatomic molecule is just a special case of a linear molecule. We must memorize the definition of z-axis in a linear molecule, because then we use several concepts which include z-axis. Number of nodal planes which contain the z-axis is equal to lambda. Nodal planes which contain z-axis are such planes. Here, a page is a plane. All right? Just extend it to all sides. It's a plane. This plane must contain the entire z-axis somewhere on it. There are infinite such planes you may construct. All right? But just by rotating the plane around the z-axis. This rule says that molecular orbitals have nodal planes. The number of nodal planes of each type, sigma, pi, delta, is given by this rule. So, sigma planes have no nodal plane of this type. Pi molecular orbitals have, because pi means lambda equals 1, pi molecular orbitals have one nodal plane. Delta molecular orbitals have two nodal planes. This rule is useful because when we construct molecular orbitals and then examine how many nodal planes they have, by knowing the number of nodal planes, we can decide which type it is. Is it a sigma type? Is it a pi type? Is it a delta type? For that reason, this is useful. Now, let us come back to here. We have discussed exact properties, which can be obtained without explicitly solving this equation here, by noting that this Hamiltonian commutes with LZ, which tells us that the solutions of this, exact solutions of this equation must be eigenfunctions of LZ with eigenvalues m, and then we have introduced the notation, lambda notation. When we come to the actual calculation here, solving this equation is difficult in the sense, and the reason is because there are two centers. We have just one electron, but two nuclear centers, and that makes it more complicated. We must use approximation methods. Approximation method for solving the molecular orbital equation is to express express the molecular orbitals as a, or in terms of atomic orbitals centered on each nucleus. The atomic orbitals available are one s, two s, 2px, 2py, 2pz, and so on. These are the atomic orbitals. Atomic orbital centered on nucleus A means like something like this. Say an s orbital is indicated by this polar graph, and this is an s orbital which is centered on center A. This one we indicate with the letter as S sub A. Of course, there are many s orbitals. 1s, 2s, 3s, 4s, etc. All of them look like similar to each other, at least qualitatively. So whether this is 1s, 2s, 3s, an orbital centered on A, an s orbital centered on A looks like that. Let us make this concrete. Suppose this is the 1s orbital, then a 1s orbital which is centered on center A is indicated by this symbol. Similarly, the same s orbital but centered on the other center, on center B, is called an s orbital on center B. If this is the 1s orbital, we will write it as 1sb. Now, simplest approximation for the lowest energy MO is we take the lowest energy atomic orbital for each center. One is 1s orbital on center A, the other is 1s orbital on center B. We combine these in a linear fashion, which means multiply the first one with a coefficient, multiply the second one with another coefficient, and add. This is the simplest approximation or lowest level approximation for the molecular orbital here, which is expected to give the lowest energy. Such expressions of this form, which means a coefficient times an atomic orbital plus another coefficient times another atomic orbital. These are called linear combination of atomic orbitals, or short for it is LCAO, linear combination of atomic orbitals. This is the simplest expression for LCAO. Better expressions are available if you add extra terms here. A third coefficient times another orbital, another atomic orbital on center A, plus another coefficient times a new atomic orbital for center B, and you may continue like this. The longer the expression, the better is the result. This has just two terms, non-zero terms. This is the lowest level approximation, which means this will give the energy you will obtain with this expression is going to be not very good. But qualitatively, and to keep it simple, I will use just two terms in the expression. All right. Now, here the unknowns are the coefficients. One is C1, the other is C2. Now, to find the relative values of the two coefficients, we may use a symmetry property of this the exact equation. Let us note the following. Here is center A, here is center B. This is z-axis. The distance between the two of them is r. And in this Hamiltonian, we have just one electron. Let us say this is the electron. What is the name of this molecule? We have two protons separated by some distance and just one electron moving around it. What is this molecule? Symbol for the molecule. This is H2. This symbol indicates neutral molecule, isn't it? Which means how many electrons are there here? 2. But this one is similar to H2 as far as the protons are concerned, but there is just one electron. So what's the suitable symbol for this problem? H2 plus cation, isn't it? Because, so, this is the exact Schrödinger equation for H2 plus molecule. Now, is this proton same or different than this nucleus? They are same. They are both protons. Their nuclear charges are the same, +1, +1 on both. Consider the geometric midpoint. If you take this point, O, and exchange the two nuclei relative to this point, take this proton here and this proton there, does the nuclear environment change? It means H2 plus. If you interchange this hydrogen with this hydrogen, can you distinguish the situation after exchanging? No, why not? Because they are both same hydrogens. Such properties are called symmetry property. So this molecule has a symmetry. H2 itself also has a symmetry, but H2 plus is also a symmetric molecule with respect to the center. This geometric center many molecules have such interesting geometric centers. This geometric center is called inversion center. Any homonuclear diatomic molecule has an inversion center. Say, oxygen molecule, O2. Here is oxygen, here is oxygen. And the inversion center is the geometric midpoint between the two oxygen atoms. Or nitrogen molecule, any homonuclear diatomic. These are inversion centers. On the other hand, if we have a heteronuclear diatomic, say HCl, does such a molecule have such a property? Can you find a point between the two such that when you exchange the two atoms on both sides, do you get the same nuclear configuration? If you exchange with H with Cl, you get Cl on this side, H on that side, and that will be a different nuclear configuration or nuclear arrangement than the starting one. So only molecules which contain similar type of atoms on one side as on the other side have such property. I can give you a polyatomic example about inversion center. Let us take acetylene molecule. It has a linear structure. The arrangement of the atoms are H, C, then C, then H. I'm not indicating, the lines here are not indicating relative distances, but what is important here is that all these atoms lie on the same line. Now, is this CH bond length in the normal molecule in acetylene, is it same or different from this CH bond length? Same. So, in this case also, the geometrical midpoint of the molecule is this point between the two carbons, exactly middle of the bond here. This is also an inversion center for this molecule. Why? Because if you exchange the atoms to the right of the inversion center with those atoms which are on the left of the inversion center and redraw the molecule, it will be identical to the starting one. So that's an inversion center. Now, what is important about inversion center? Why are we discussing this? I'm going to explain to you the mathematical definition of inversion operation. Say we have a point here. This electron has Cartesian type variables x, y, z. Its distance to nucleus A is r sub A. Its distance to nucleus B is r sub B. The potential energy expression for this electron, remember each nucleus here is a proton, which means +1 charge. The potential energy expression is minus 1 over Ra minus 1 over Rb. Now, taking a point x, y, z and making the replacement x into minus x, y into minus y, z into minus z. All variables are converted into minus their original values. This is called inversion. Inversion operation. Now, graphically, inversion operation corresponds to this. Draw a line from the point, a straight line, which passes through this inversion center and extend it to the other side. Then note the distance between the original point to this center and proceed to the other side by the same distance. So, for example, this looks like the new point. The coordinates of this point are minus x, minus y, minus z. Our time is up. It looks okay, we have to stop here.